Okay, so I understand that um, electrons are being categorized into shells, subshells, and orbitals.
Hmm.
Um, but it seems like there's a lot of overlapping between those terms. And as I understand it, the electrons are they're classified into these shells, but they don't the shells don't describe the position of the electron. They describe the energy level, right?
Right. Although we do take the energy level, and which is known as shells and subshells and all that stuff, and we do categorize them, which is what we're in the middle of doing right now, actually.
Uh-huh. And so I guess even though they're categorized in that way, you could say that the closer the subshell is to the nucleus is actually a general. You could say that it is that in fact that close to the nucleus because it has less energy than an electron in the valence shell. Does that make sense?
Yeah. So, you know, if you look at shells, right? I was just going to
Yeah.
review this. So it's just a general volume where you find electrons.
Yes.
So here's an equation that describes how many electrons can be in a shell.
Yeah.
And it also tells you how many subshells there will be. So we have
Yeah.
seven
I found it confusing.
shells. Shell number one is closest to the nucleus, so it has the lowest energy,
Yes.
right?
Yes.
And so it is talking about energy, but in our brains, we don't have a place for energy, so we have to think of a place. So that's why the shells, subshells, and orbitals.
Uh-huh. So if it, you know, when comparing shells and subshells, um, I couldn't, is that referring to the total number of shells?
Um, well, like if you look at what this number two does here, right? So
Yeah.
n tells you the maximum number of subshells. So if n is equal to 1, there's only one subshell. If n is equal
But
to 2, then it can be categorized in two different subshells, the 2s and the 2p.
So would carbon be considered N? I mean, hydrogen, would hydrogen be considered N?
Well, n just stands for a shell. And if you look at the periodic table, a shell is a period.
Each row, right?
Right. So here's shell number one. You
Yes.
can get one electron that would describe hydrogen, two electrons that would describe helium, and now that shell is full.
Right.
You got more electrons to put in there, they got to come out in shell number two.
Yes.
So here's 2s1, 2s2, so that's the first subshell. And the second
Yes.
subshell is over here, which are p's. So 2p1 all the way to 2p6. And then we have only 7 shells, although they're
Right.
trying to make the 8th shell, but they haven't been successful yet.
I have one more question here. It says N is the maximum number of subshells, but then in the paragraph prior to number one, it says the shell is given the symbol N.
Right,
So N represents the shell, but also the maximum number of subshells.
right. So n is a number, and that number specifies how many subshells are possible.
So if there was 7 shells, in theory, there could be 7 subshells.
Yes, in that shell.
Gotcha.
Okay. Okay, thank you.
So keep in mind, this is all statistically driven, okay? So what I tried to do here is organize the whole thing in our heads. So we only need 4 types of subshells. And the reason is there's just not that many elements. I mean, you could take n and it could go to 1,000,000. You could take 1,000,000 and put it into 2n squared. You still get numbers, right? So that's all mathematical. But we only have a small part of that was applicable because we don't have that many elements. So it turns out we need to use only 4 subshells. And in a few minutes, you'll see how those are organized on the periodic table. And so what's not really mathematical is the designations that they gave to the subshells. That has to do with something that they were working on but didn't turn out to be very important. But let's look at the number of orbitals. So an orbital is the wave function, right? The most specific volume. Look at how they occur. 1, 3, 5, 7. Now most books never go past this because they're not interested in you understanding the whole system. But if you look at this right here, isn't it consecutive odd integers? The next one would be 9. See how that works? You could go on forever. Then they get the maximum number of electrons that can go into that orbital. How are you getting this column? You're simply multiplying everything by 2. So in an F type of subshell, you can have up to 7 orbitals and up to 2 electrons in each orbital. So that would give you 14. And I'm going to relate this back to the shapes that we looked at. Those are the shapes of the orbitals. So the shape of a single orbital for an S is spherical. If you keep putting spheres together, it's still spherical. The shape of a single P orbital is a dumbbell shape. It's got 2 lobes with the nucleus in the center. And you can have 3 of them, right? 3 of them. Put those 3 together, become semi-spherical. Then you get more and more complexity. A D, which can have 10 electrons in it, is basically a double dumbbell. Then it gets more complicated and more complicated. You start putting these shapes together, it just simply gets spherical. But that is not the way the electrons move. We don't know how they move. It is not how the orbitals are shaped. And so we get into the situation now where we're comparing the energy of a F and say a D. Well, guess what? Those are different animals. It's really hard to compare electrons in this kind of an orbit compared to this kind of an orbit. So all the ones that we don't need, I put in green. Spam risk.
I have
So
a question.
Yeah.
Sorry. What exactly are we comparing between these subshells? Like the amount of energy that each subshell has?
Essentially, yeah.
Okay.
So here's what I did to try to organize this for you. So in shell number 1, you can have only 1 subshell. That's an S. How many electrons can you get in an S? 2, and now it's full. So look, 2 times n, when n is 1 squared, gives you 2. Then shell number 2, you can have 2 subshells, an S and a P. You can get 2 in an S, 6 in a P, so that's 8. Look, 2 times 4 is 8. See how that works? We're just following this. In shell number 4, you can get 4 in there. That would be 32 electrons in there. Shell number 5, you could have 5 subshells, but we don't need that 5th subshell because we don't have any elements to go into it. Theoretically, you could have 50 electrons just in that one shell. If you look at shell number 7, you could get close to 100 electrons in there. That would account for 98 different elements, and the whole periodic table has only 118. So all this capability that is mathematical is not necessarily needed. We only need the ones I left in black. So here's the 7 shells on the periodic table. you can see that shell number 1 fills up very quickly because it's small, it's close to the nucleus. Shell number 2, you can have 2s1, then 2s2, and now it's full. So then you got to put electrons into the p. So while we're at it, you can see the organization now. So here's your 7 shells. Here's the 4 subshells. The S's here, the P's over here, the D's over here, and the F's over here. And notice that we took this out from right here. And this is actually shell number 4 and shell number 5. So I also tried to put in here, you can get 2 electrons in an S subshell, they're spherical. You can get 10 in a D, they're more complex. You can get 6 in a P, there's 3 of those. You can get up to 14, and they're complex subshells. So now, here's the thing that confuses a lot of students, but fortunately not you guys. It's the Aufbau principle. So what Aufbau essentially means is that if you had a nucleus and no electrons, and then you started just adding electrons one by one, where would they go? They would go in the lowest energy orbital first, closest to the nucleus. Okay, so Aufbau means the building up principle. And so here's how we get the same order that's on the periodic table. Because what we're trying to do is understand how the periodic table works. So, see how I made this diagram right here? It's really, what's the word for a mathematical, not a field, array. So here's the shells, right? Shell number 1, I get the 1s, it's done. Shell number 2, I got the 2s, the 2p. Shell number 3, the 3s, 3p, 3d, right? You can understand how this was put together. If this right here was missing, you'd be able to figure out what it was, right? So it's a mathematical array. But we're so used to reading from left to right, we expect everything to follow left to right. In this case, it doesn't. To match the same arrangement that's on the periodic table, we have to take the first diagonal right here and then make all these diagonal lines that are parallel to it. So that actually gives us the order of filling on the periodic table. So the Aufbau principle are those arrows in blue. So what comes first? 1s, and then 2s, and then 2p, right? Then 3s, and then 3p, 4s, and then 3d. So notice I get this order, and that's the order of energy. Energy increases going this way. Make sense so far? So now here's the thing that messes people up. Why is the 4s coming before the 3d? Why is the 4d coming before the, no, the 5s coming before the 4d? What the heck is going on there? Well, you're gonna have to let go of your tenacity to the numbering system. If you're comparing a 4s to a 3d, are those apples and oranges or apples and apples? They're not the same, are they? So an S is a spherical orbital. D's are multiple. They're complex. There's 5 of those, right? There's only 1 of these and there's 5 of those. So the situation that we're put into is like, oh my God, how come 4 has become 3? That doesn't make any sense. And I learned that in, kindergarten or something. But the difference is S's and D's are not the same thing. So what it
What
means,
is F stand for?
what?
What does F stand for?
F is another type of subshell. It's multiple,
Oh, okay. I see. I see.
multiple, yeah? Okay.
Yes.
You
yes,
go back to
thank you.
here. Oh, wait, no. Here, right?
Okay. Okay. Thank you.
So look what happens, and you can take your periodic table and follow along here. So it goes 1s, and then 2s, 2p, 3s, 3p, because these are the p's, and then you come 4s, and then 3d. Look on your periodic table. That's what it says right there. Scandium is 3d1. That's just the way it is on the periodic table. So then you end up getting 4p over here. So that is the same order that we get here.
So as we follow these subshells, like if you were to scroll up a little bit on the periodic table, as you're going, like let's say you're from at 4s2,
Uh-huh.
that compared to 4p6 has a lower valence electron energy. Is that like what it's kind of trying to show us?
No, don't use the word valence right now.
Okay.
Valence are just the ones on the surface. We're looking at all the electrons. So yeah, 4s is a lower energy than 3d, and it's a lower energy than 4p.
Gotcha. Okay.
Because the off-bow principle is we start here and we simply add electrons and they get into more and more energy. So the ones that are way out here are high energy. So the first thing is getting you to accept that this is okay. So that's the important thing, that it's always on. The off-bow principle is what's on the periodic table, and that's what we care about. There are textbooks that switch back and forth between off-bow and not off-bow, and it's just like, what are you doing to the poor students? So if you really wanted to take your periodic table and understand how it works, I would suggest finding shell number 4. So in shell number 4, you can have 4 subshells, right? Where are they? Well, here's the 4s, here's the 4p, here's the 4d, where's the 4f? It's way down here. And so why are these separated like this? Because that's the off-bow principle, right? 3p and then 4s, that's exactly what's on the periodic table. Then the 3d is in between that and the 4p. Then you have to go through the 5s and then finally the 4d, or not finally. Then you got to go through these before you get to the f's. Okay. So I'm going to try to explain it to you a little bit. It's called orbital overlapping. And so here's shell number 1. Shell number 1 is small, it's just an S. Then shell number 2 is bigger, there's more electrons in there. So you can get 2 in there, you can get 6 in there. But they repel each other a little bit. There's repulsion here. So even though they're all attracted to the nucleus, they have repulsion in between them. So it turns out that shell number 2 is split into 2 subshells. And shell number 3 that I put in blue is split into 3 subshells. There's more electrons in there. It's going to take up a larger volume, right? So then when I put shell number 4 over here, there's even more subshells, and there's even more spread out because there's more electrons and you have less repulsion between the different subshells. So it just so happens that the 3D is a lower energy than the 4P. And the 4S is a lower energy than the 3D. And then the way I drew these is the way you're thinking, as if they were all sphericals. as if they were all apples. But that's not what we have. See, they're totally different animals. So we can't easily make that comparison. And here's another explanation for this. So in chemistry and physics, one of the concepts that's often used to explain things is vibrations. And so say this is a stick right here. Shell number 1 is just a stick with very low energy, and it's not split. Shell number 2 is a higher energy shell, so you go up higher energies, right? You hit that stick, and now that stick is vibrating back and forth like this. So what we have is this might be 1 at the bottom, the lower energy, and then this will be vibrating to the higher energy. Looks like a tuning fork, doesn't it? In shell number 3, you hit that stick even harder. So when it starts to vibrate, there's a part where you can see it down here, you can see it up here, and sometimes you see it right here as it transitions between that way and that way. And then shell number 4 splits even more. And so if you go up now, you'll see that you start to get overlap between these energy levels. The 4s is a lower energy than the 3d. And again, they're apples and oranges. That's the reason why that happens. So hopefully you believe that. And with that, we're going to move into like what I call 7 major points about the electron configuration. Now, if you look at the periodic table, say, what's a good one to look at? Let's just look at scandium. Okay. See scandium right there? Maybe it's too shiny. Let me just get the other one. So if you look closely at scandium, you expect to see 4s and then 3d, but you don't see that. You see the 3d and then you see the 4s. And maybe you should be thinking, oh my God, that's not following the Aufbau principle. And you're right. This particular periodic table, which in my opinion is the best one, you cannot simply look under the name or right above the name and just write down what you see, because that's not the Aufbau principle. What they're doing is simply reading from left to right. That's what they're doing. Okay. So why would they do that? When I first noticed it, I'm like, God, they're just messing everything up. Well, here's the logic. Here's the reason why they're doing that. That helps you find which electrons are the valence electrons. So here's an example using bromine. So bromine has 35 electrons, right? How are they arranged in the atom? Where did I get this order right here? This order is simply, here we go now, this, right? Using the Aufbau principle, which is the same thing you see on the periodic table. So why would they write it differently? Here's the reason. Bromine is in group 7, so it has 7 valence electrons. So what are those 7 valence electrons? Well, you would have to remember that the valence electrons are in the highest numbered shell. They're not simply the last electrons that you see on the Aufbau principle. So in this case, they're split from one another. Okay? And you may be asking the question, why? Well, it's not exactly logical when we try to explain it. But nevertheless, which are the 7 valence electrons for bromine? They are not the 4s the 4p5 and then you take 2 out of the 10. No, you're taking 2 out of here. Those in blue are the valence electrons. And now what if you did it like what's on the periodic table, where you just go like this? When you do that, look at where the 7 valence electrons show up. Right there at the end. So the reason why they do that is they're trying to help you figure out which ones are the valence electrons. So then another point. We have 3 different ways to show the electron configuration. We're all going to use the Aufbau principle all the time. So we have the complete or total electron configuration. We have the noble gas shorthand method. And we have the generalized group, electron configuration for all the valence electrons in that group. So here's an example. Magnesium. It's element number 12, so 12 total electrons. It's in group 2, so it has 2 valence electrons. Where are those valence electrons? Right there, in the highest numbered shell. Give the noble gas electron configuration for magnesium. And this is what's on the periodic table, actually. If you look at magnesium, that's what you see. So it has everything that neon does, but in addition to that, it has 2 electrons in the 3rd shell in an S-type of subshell. So neon is a noble gas, and it simply replaces the electron configuration of that noble gas with its symbol. So what if we do the same thing for radium? 88 total electrons, but it's also in group 2, so it has 2 valence electrons. So here's the Aufbau order, right? With the complete electron configuration. Which ones are the valence electrons? The ones in the highest numbered shell. So to give the noble gas electron configuration for radium, turns out that all of this right here is the electron configuration for radon gas. Does that make sense? So you should like this method. You simply write the symbol instead of all this stuff. So now that we've looked at 2 elements in the same group, what can we say about the generalized electron configuration for the valence electrons? Look, that was 3s2, that was 7s2. If you look carefully, every single element in that group has 2 valence electrons in an S subshell. They're all S2. So why do they have similar properties? Chemical properties are all about the electrons, aren't they? And are they going to be the electrons on the surface or the electrons buried next to the nucleus? It's going to be the electrons on the surface that interact with other atoms in the environment. Those are the ones that are going to be reactive. You can lose them, you can gain more, you can share them. And so here's some examples of some nonmetals. So sulfur is element 16, so you have electron configuration. There's the total electron configuration. It's in group 6, so therefore it has 6 valence electrons. Which ones are they? Well, they're the S2, the 3s2, and the 3p4. And this represents the noble gas neon. That makes sense? What about tellurium? 52 total electrons. And I get students sometimes like, mean, you're going to make us write down the whole thing for 52 electrons? I said, yeah. And why not? So that's how we would distribute the 52 electrons using the Aufbau principle. And it's also in group 6. So what are the 6 valence electrons? Well, they're in the highest numbered shell. So that would be these two right here, right? And what about the noble gas electron configuration for tellurium? Okay, so all of this right here represents krypton. So I have krypton, and then what's after krypton? The 5s2, the 4d10, and the 5p4. So now if you were to take a quick look at what your periodic table actually has, it will not do the Aufbau order. It simply goes 1, 2, 3, 4, 5, 6, 7. So it'd be 4d10, 5s2, 5p4. So now if we look at all the elements in group 6, what do they all have in common? 6 valence electrons. And how are those electrons arranged? They're s2p4. So if your natural valence electrons are shared, are s2p4, and that's shared with all the elements in that period, that group, they're all going to behave the same. So I can look at any one of those elements from that group and say, oh, you're s2p4. I can almost predict what you're going to do. You're going to want to take 2 electrons from somewhere else, either by forming an ion with them or forming a covalent bond, because you want to be s2p6. You know why? Because all the noble gases, except for the runt of the family, which is helium, they're all s2p6. And those represent chemical stability. So here are, yeah, go ahead.
Isn't it 5p6? Isn't tellurium trying to become 5p6?
No, but to generalize is not what shell they're in, right? It's just like, what is their arrangement of their valence electrons? So everything in group 1 is S1, everything in group 2 is S2, and everything in group 6 is S2P4. Everything in group 8 is S2P6, except for helium, which is the runt of the family.
Okay. Gotcha.
So here's for neon. If I took an electron away from neon, would it be happy? No, it would try to get that electron back at any way it could to become happy, because S2P6 really represents happiness. So sorry to use psychology on the periodic table, but group 8 is happiness, and everybody wants to be there. What about radon? Well, that's a big one, okay? So 86 total electrons, so here's how the arrangement would be. Notice that what comes after the 6s2? The 4f. How do I know that? If you're looking at the periodic table, it's pretty hard to discern that. But if you go back to the Aufbau principle, that's how you would figure that out, right there. So there may be cases when you're trying to do homework problems or something, you need to draw this out so you can figure out what this is. This is kind of an interesting principle of learning things. Do I memorize this? What's that going to do for me? Or do I memorize this? And when I say memorize, am I really memorizing, or are I just remembering how the system works, the theory? So this is the theory. I don't have to memorize this. Okay. So then the third point is representative metals react in order to get a noble gas electron configuration. Okay, I put representative elements, I should say. Well, what do metals do? Metals lose valence electrons to become isoelectronic. That means the same electron configuration. It doesn't have anything to do with the nucleus. So they don't change from one element to another, but they just change electrons. So metals like to lose electrons to be like the nearest noble gas. So let's look at magnesium again. Give the complete electron configuration for the magnesium ion. So if you look at magnesium on the periodic table, you'll see that its electron configuration there, but you also see the oxidation number, which is right above the symbol. It's only a 2. That means that the only oxidation number, the only ion that's ever been observed for magnesium is to form the +2 ion. What does that mean? You start off with 12, you lose 10, that means 2, you have 10 electrons left over. Here's the ones that you lost, the ones that were in the valence orbitals. So I prefer to write it this way. Most textbooks write it this way. It's just disappeared now. Here I'm saying it's there, it's just empty. Here they're saying, oh, it's not here anymore. Well, it is there. So when you do the noble gas electron configuration, I would prefer to do it this way, but that's what you mostly see. Well, what about radium then? Okay, it also does nothing more than form the +2 ion. You can see that there. Okay. So what does that mean? It's got 88 as an element. It loses 2 to form the ion. It has 86 electrons total. Here's what I would get. Where did the 2 come from that it lost? Well, it's not going to be in these core electrons. It's going to be from the outermost electrons, right? So I would leave that there. Same with noble gas electron configuration. I think that's preferable. And so here's kind of what we're doing. Here's magnesium. And is magnesium stable? Well, the answer is magnesium is not that stable. If I take elemental magnesium and I leave it out in the atmosphere, it starts turning color, starts turning into a gray powder of magnesium oxide. It's reactive. What happens when it loses those 2 electrons? Now it has the same electron configuration as neon. And neon is a noble gas. It's extremely stable. So by losing those electrons, it becomes electronically stable. Same thing with radium. So what about nonmetals? Nonmetals gain valence electrons to become like a noble gas. So now, here's what takes a little bit of thinking here. Here's all the oxidation states for sulfur. You see a whole bunch of them, right? Which is the only one that represents the sulfide ion? What does sulfur want to do? I'm having a hard time holding this, sorry. Sulfur's right here, so it wants to gain 2 more electrons to become like a noble gas. It's going to become like argon. It won't become argon because protons aren't gained or lost. So if you look at sulfur, it has a 6, a +2, a -2, and a +4. The positive numbers are useful when it binds to more negatively charged atoms, but not when forming an ion. So what is sulfur going to do? It's going to be going from S2P4 to become S2P6, and that makes it stable. What about the tellurium ion? Okay, the same thing. It wants to gain 2 more electrons, so it can go from S2P4 to S2P6, which is stable. So now we looked at what metals want to do, what nonmetals want to do. So that helps us explain why chemical reactions happen and why elements react to form compounds with only certain formulas, which is really the law of definite proportion. So here's an example. It's really something we're going to be doing in the next chapter. And look at the way I worded this. Predict a compound formed between sodium and sulfur. Because that's what really science is about, predicting what's going to happen. Why do we study hurricanes? Not because we can say, oh yeah, that's a level 5 hurricane that's beating the crap out of us right now. Aren't we glad we know that? No, it's because we can predict the behavior so we can be prepared and understand things. So here is the complete electron configuration for sodium. And what does sodium want to do? Is it happy or is it reactive? It's reactive. Sodium, in fact, is so reactive. If I had sodium metal and I just toss it into water, it would essentially blow up. It makes a chemical reaction with the water that ends up producing hydrogen gas and enough heat to cause that to explode. What about sulfur? Sulfur is not happy either. It's S2P4, it wants to become S2P6. So guess what? Sodium wants to get rid of electrons. Sulfur wants to take electrons. If they get together and they do this chemical reaction, they will become more happy. So this is what sodium wants to do. Form the +1 ion. This is what sulfur wants to do. Form the -2 ion. So you let them do what they want to do to be happy. And now they just happen to be oppositely charged from one another. So they will be attracted to each other. It's going to form an ionic bond, isn't it? So the other thing we need to understand is that all compounds must be electrically neutral. So if I were to put these two together, just like how I did up here, and they'd be attracted because now they're both happy, that's not electrically neutral. That would have a charge of -1. So one of the tricks that we do is we take the 2 and put it down there, take the 1 and put it down there, and we get this. That means that there's 2 sodiums, so there's a total of +2 charge. There's 1 sulfur, a total of a -2 charge. That gives us the neutral molecule, which is this. And then we could even name that, because you know how to name sodium chloride. So what do you do to the name of the metal? Nothing, you just write it down. And what do you do to the name of the other one? Chlorine becomes chloride, so sulfur should become sulfide. We could predict that that name should be sodium sulfide. So I'm trying to look, give you previews of what you're going to be learning so that, you get a perspective on it and you see that it's not like just memorizing all kind of tiny, tiny, tiny things. It all works together as a system. Okay, so questions so far? Okay, well, the fourth point I want to make is that the non-representative elements, which really are metals, the transition metals, what's their problem? Why are they acting so weird? It's because most of them can never become like a noble gas. Never. They will never become happy. Oops.
Oh, Professor, I actually have a question. How come towards the middle of the transition metals, it goes like 6, 7, 8? So like, why aren't the 8 like iron, ruthenium? Like, how come they aren't stable? Do they end up getting 8 electrons?
They are not S2P6. They're S2D6. And you'll see what that means in a minute. But let's take iron, for example. Iron is a metal, so it has to lose electrons, right? How many would it have to lose? It would have to lose, I don't know if you can see this, 1, 2, 3, 4, 5, 6, 7, 8. I mean, like a noble gas. You can't lose that. Imagine you have a neutral oxygen atom there. It's neutral. I grab onto an electron and say I just forcibly pull it away. Now that's positively charged. So I grab onto another electron. Now as I try to pull that electron away, what's happening? The positive charge is making it that much harder for me to pull it away. So the result is I can take 3 electrons away sometimes, maybe at the maximum even 4. After that, I cannot take any more away. The attractive force is just too strong. There's no way iron is ever going to be able to lose enough electrons to become like a noble gas. Well, what if iron tried to be like a metal, a non-metal? Say it tried to gain. It would have to gain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So again, say you have neutral iron, and I take an electron and I bring it close to that neutral iron atom. What's the immediate response? Electron clouds on the surface are going to be trying to repel that new electron. But say I get it on there. Now it's a negatively charged anion. The next electron I bring, it's going to be repelled even that much more. So for some elements, I can get 3 electrons on there, maybe 4, but that's about it. But you see, iron has no way to ever be like a noble gas, no way to ever be stable. So if that's the case, then say that was you, because I mean, you know people that will never be happy, right? If you have no way to ever be happy, what would you do in life? Maybe you simply wouldn't do anything, because no matter what you do, you're not going to be happy. And many of the transition metals actually have that behavior. Think about the jewelry metals, titanium, gold, platinum, and all those ones, right? That's one response to never being able to become stable, is you don't do anything. I'm sure you've known people like that. Another one is you simply oscillate back and forth between quasi-stable forms, never quite happy. And that's essentially what iron does. So iron, if you look at it on the periodic table, most have a 2 and a 3. Some also have a 6 there. The 6 is not possible for an ion. That's only when it forms certain compounds. So most periodic tables have only a 2 and a 3. So that means that iron can lose 2 electrons. And when it does that, is it happy? No. Sometimes it loses another one. And then does it become happy? No. So it simply bounces back between those 2 quasi-stable forms. So here's iron plus 3. If it were to gain an electron from somewhere and form the plus 2 ion, neither one of these is going to be happy. But now nature takes advantage of these idiosyncrasies. Iron is one of the most important elements in nature, or in life, I should say. And so all excitable membranes, all oxidative processes, mitochondria, everything else totally depended upon iron. So here's essentially how the mitochondria works. So iron is situated into a protein. It gives the protein color, just like it gives color to your blood, since iron is in the hemoglobin, right? And that's what gives it the color. So sitting there in the plus 3 state, sequestered within this protein, something comes along and gives it an electron, and it turns into the plus 2 ion. Is it happy? No. It doesn't care to keep that electron, doesn't do it any good. So it kind of turns around and hands that electron off to another protein with an iron in it. Meanwhile, that process right there ends up pumping protons across the membrane in one direction. What that does is it creates an electrochemical potential across that membrane that can then be taken advantage of by the ATP synthetase protein. So when protons come back into the mitochondria, they have to come through the ATP synthase protein. And that is what the protein uses to take ADP and phosphate and squeeze them back together again, making ATP for you. So what would happen if you were iron deficient in your body? What would be the effect on your mitochondria, on your ability to make ATP? It'd be kind of devastating, wouldn't it? That's why in parts of the chapters here, I'll be talking about iron deficiency. I think it's one of the most important problems in modern day nutrition. Most people don't know it, but they're walking around iron deficient.
So you're saying that there's a correlation between iron and mitochondria, like in our body?
Oh yeah.
That actually makes a lot of sense. Especially because my mom is anemic. You know, she doesn't have that much iron, and she can always be very tired and stuff, especially when she doesn't take her iron.
And this is the reason why I got into research on chronic fatigue syndrome, because I took my knowledge of mitochondria and all that kind of stuff, and I applied it to that particular disease. But I couldn't find a really good correlation, but I tried. But yeah, we know that iron deficiency is extremely important. We had a master's student one time. He subsequently got a PhD. But for his master's degree, what he did is he went through and he looked at all the enzymes that are dependent upon iron. So we were expecting dozens. He came up with basically hundreds. So, yeah. We'll be talking more about iron deficiency. So then, what do the non-representative elements do? They may not obey the rules, but they still lose valence electrons from their highest numbered shells. If we looked at what they normally do, because they can't be like a noble gas for the most part, what they normally do is they'll do whatever they need to do to either get a completely full or completely empty subshell. So let's look at some examples. And by the way, this is extremely difficult to do. I wouldn't give you anything on an exam or anything, or even homework, without giving you some guidance to help you figure it out. Here's mercury. Okay, if you look at mercury, the oxidation numbers are a 1 and a 2. 2 is bold, so it's the most common. And so it's going to lose either 1 or 2 valence electrons. Here's where the valence electrons are, right, in the highest numbered shell. So if it forms a +1, I have to take 1 out of that valence electron shell. Notice that even though this is partially full, that's completely full, that's completely full. If I take 2 electrons from mercury, this is the more stable ion, this is what I get. So now this is completely empty, and these are completely full. Does that make sense? And I will always use that red arrow there to show you that I'm keeping this as a placeholder. I get really irritated when I see textbooks just leave it out. You know, it's just like, you know, teaching is about communicating. If you're not going to communicate, then don't teach.
Because it would imply that it's just disappeared or something.
Exactly. Totally confused people.
That would be super confusing.
Yep. Now let's think about mercury for a minute. You have experience with mercury. It's in thermometers, it's in barometers. Barometers are always exposed to the environment, at least a little bit. So right there, it's kind of like, this is the transition metal. It's right in the corner of it, right? It's almost not even a transition metal. But what do we know about it? It stays silvery and shiny for a really, really, really long time, because it's kind of reluctant to do this. Doesn't make it like a noble gas, does it? So it's reluctant to do it, even though this is what it does. So here's titanium. Here's the electron configuration for titanium. And here's the oxidation numbers, 4, 3, and 2. So here's the 4. Notice that it took all of its valence electrons and got rid of it. And now it is like a noble gas. So titanium, which is right here, okay. If you look at it, loses 4 valence electrons. It's like a noble gas, isn't it? It's like argon. So that is the most common thing that it does, because that's electronically stable. It's like a noble gas now. But if it forms a +3, how would we be able to figure that out? Well, if I take 2 from there, that completely empties that, and I leave 1 in there, well, guess what? That was never full in the first place, right? If I got to take 2, I might take it from here. If I got to take 4, I take them all, so they're all empty. If I got to take 3, if I empty this out totally and take 1 from there, that kind of makes sense. Okay. But anyway, do you really need to know how to do this? Not really, especially for Chemistry 100. I'm just showing you the logic, what they do. And remember, we need to understand the representative metals. We don't need to understand what the non-representative metals do. But the non-representative metals do follow certain behaviors, which are logical. So here I did it for iron, then I did it for lead, and you can see that there is a logic there. So in every case, if I left something empty, I didn't just let it disappear. I put it there, and I put the red arrow there to bring that to your attention. So why would the lead-4 ion be particularly stable? Completely empty, completely full, completely full, completely empty. What about the lead-2? Completely full, completely full, completely full, completely empty. Then the sixth point I want to make is that there are exceptions to the rule. There's always exceptions to any rule. So you don't have to be responsible for trying to explain this. I just want you to realize that there's exceptions to the rule. And I think it's important that I point these out, because if you're looking at the periodic table and you're going through trying to figure out, oh, make sure everything follows the rule, and you find something that doesn't follow the rule, you're like, oh my God, I don't even know what the rule is anymore. So about the first one where you see an exception is with chromium. So here's what the off-bow or the theory would say. It would be 4s2, 3d4. But this is what you find on the periodic table. Like, what? Why the heck would it do that? Guess what? You don't have to explain that. If you want to become a graduate student in chemistry and concentrate on electron configurations and reactivity, then you better need to explain this. All we need to know is that exceptions happen. Copper is another one. Niobium is another one. There's a bunch of other exceptions. And now where it really becomes important is right at the transition on the periodic table, where we take out the F subshells and put them in the lower over here. Why did they take them out there? Well, if you look at lanthanum, here's what the off-bow principle would predict. 6s2 and then 4f1. Then if you look at the next one over, 6s2, 4f2. Hey, that makes sense according to theory, doesn't it? But what do you see on the periodic table? What the heck is that? That's a total exception to the rule. And it happens at the worst place imaginable. But according to theory, it's really logical that they did it that way. But the experiments show that the theory isn't followed by those elements right there. And that's shell number 4. Shell number 5, right below it, here's the theory. 7s2, 5f1. 7s2, 5f2. Makes perfect sense. But look, the theory doesn't match the experiment. But don't be upset about this, because all the representative elements obey the off-bow principle, all of them. And 3/4 of the non-representative elements follow that off-bow principle. So there's just some exceptions, that's all. So questions so far?
I have another question.
Mm-hmm.
In a sense, since the noble gases, they're they don't really do anything. They don't really react.
Uh-huh.
In a sense, doesn't like iron and like gold and platinum, they don't really do anything either. So in a sense, aren't they stable?
Well, you can make them do stuff. When we
Oh,
say it just sits there and doesn't do much, what we're really referring to is, does it respond spontaneously to oxygen in the environment?
yeah.
So if I put nitric acid in the environment, hey, they're all going to respond. You know what I mean?
Oh, I see. Okay. Okay.
But the noble gases won't.
Right. Okay. So it's like the concentration of the oxygen.
Yeah, oxygen is very reactive, but there's other things that are more reactive than that. Although we don't find them on the planet, we have to make them.
Mm,
Like nitric acid, you don't find nitric acid on the planet anywhere.
got you.
Okay, so the last point, when we look at orbital diagrams, I want you to realize that this does not change anything. All it does is just add one more concept, okay? So here we have the subshells, the number of orbitals, the maximum number of electrons, and here's the box orbital designation. Now, some textbooks use circles. I just think it's easier to draw boxes because you can draw them all like that, right? So what does that mean? Every box is an orbital. So I can get 2 electrons in each of these. So 2 in there, 2 in there, 2 in there to accommodate the 6, right? And so I'm not going to bother you with quantum numbers on a test, but what I probably should do is bring up, I don't know, figure 7. Should I find that? Let me find figure 7. Hello, please open. Here we go. Where is it? Here we go. So remember, this is not on a test or anything, okay? But I want you to realize that all this stuff is mathematically derived. So notice, here's the shell numbers, right? And in the original thing, they had letters representing them, which became even more complicated for someone trying to explain it. Here's the result of 2n squared, right? So shell number 7, you can get up to 98 electrons in there. And so that's the first quantum number. And the next quantum number is called azimuthal quantum number. It basically gives you the number of subshells. So here's n is equal to 1, you can get 1 subshell, it's a 0. Here's shell 2, you can get a 0 and a 1. See how that works? The only confusing issue is that you start with a 0 instead of a 1. Then you have the magnetic quantum number, which really designates the number of orbitals. So what that means is that 0 can't be split. What does that mean? Well, that means basically there's only one entity there, which means that there's only one subshell. So, excuse me, one orbital. So if I look at shell number 2, there's a 0 which can't be split, and then there's a 1 that can be split. So you start at the 0, if you go off a little bit that way, you get a +1. If you go the other direction, you get a -1. That ends up giving us 3 orbitals. So how are the electrons arranged in shell number 2? Well, here's 2s right here. You can get 2 electrons in it. Here's 2p right here. You can get 6 electrons in it because you have 3 orbitals. See how that works? So I went and I built through the whole thing. The ones that are in blue are not even on the periodic table, but you can see it is a mathematical progression. So here's the problem now. See when we do this right here, like the valence electron for, what is this element? Sodium. Shell number 3, there's an S type of subshell, there's 1 electron in that. This right here specifies 3 out of the 4 quantum numbers. That 1 tells me there's 1 electron in there. It doesn't tell me whether it has an upspin or a downspin. And that's the 4th quantum number, is the spin-spin quantum number, that represented by the arrow. The arrow could either be up or it could be down. Okay. So, let's see. That for a minute. Get that back so I can share again. What the heck is the 4th quantum number and why do we need it? Say your name is Joe. That's 1 descriptor for you. That would probably be several million Joes on planet Earth. So we say, okay, let's give him another descriptor. Joe Smith. How many Joe Smiths do you think there are in planet Earth? Well, maybe it's only 1 million now. So what if we say Joe James Smith? I'm sure there's still going to be 100,000 of you. So that's 3 descriptors. It's not enough to talk about only you. You need another descriptor to describe only you. Say we use now your address, or we use your social security number or something like that. Then you can get it so there's basically nobody else like you. And that's what the 4 quantum numbers do. You need 4 descriptors to really describe 1 electron as being different than all the other electrons in an atom. So that's the reason why we use it. But where does that come from? As it turns out, electrons are paramagnetic. Iron is paramagnetic. That means that you can make it into a magnet. So the reason why the Earth has a north and a south pole is because we have an iron core and because the Earth is spinning. If the Earth is spinning one way, you have north and south. If it stops and spins the other way, north and south are going to be reversed. It's a similar thing with an electron. Electrons are paramagnetic. So if it spins in one direction, you have north and south this way, that's given a +1/2. If it spins the other way, it becomes a -1/2. So as it turns out, this is acceptable. This is represented by this. 1 arrow is up, 1 arrow is down. They have to have opposite spins. What you cannot see is this. You can draw this, you can draw that, but you cannot draw that because that would represent north to north, south to south. Now, does this mean that electrons are attracted to each other? No, they're repelled by each other. They're going to be as far apart as possible. But this represents so much more repulsion, such a higher energy, that they won't be allowed to stay in the same orbital. So this is not allowable. Okay? That's fine. That's fine. That's not good. So let's try to figure out what we're looking at. Why do we draw the P like this? Because that represents the 3 orbitals that's in a P subshell. Okay? And all of these are the same energy. So if I got 1 in there, and it's got 1, 2, 3, 4, 5, 6 places for it to go, it could be like this, like this, like it could do anything it wants. It could be in any lobe that it wants to be in, and that would be fine. Now, what if I have 1 more electron to put in there? This would not be allowed. You know why? Because if this electron was there already in, say, the north spin or the up spin, if I bring this electron in and also happen to be in the same spin, I would have to stop the spin of this electron and make it spin in the opposite direction. That takes energy to do that. So, what is a lower energy? Let this guy do whatever he wants to do. Let that guy do whatever this guy wants to do, and that's fine. That's fine, that's fine, that's fine. That makes sense to you? So, it's the concept of degrees of freedom. And it's a very difficult concept to explain. And I don't know whether other textbook writers actually totally understand it, or maybe they know something more than I do, but here's what I'll explain it to you. If you take a particle in a box, say it's a small box, and you give it energy, what does that particle want to do? Think about anything that you heat up. What does it want to do with that heat? It wants to get rid of that heat, right? So all matter wants to get to the lowest energy possible. So if I have a particle in a small box and it has energy, where can it go inside that small box to try to get rid of that energy? It's bouncing all around looking for a place to get rid of that energy, and it can't find any. Now what if I let it out of that box, and in this giant box, now the likelihood that it goes from here to here to here, and somewhere in that big box I'm going to find some way to get rid of some energy, that actually is a lower energy form for that particular electron. Because there's more places it can go to try to find somewhere to get rid of its energy. So electrons want to be free. So instead of taking this electron and forcing it to be in with this guy and forcing it to follow those rules, it's going to be happier anywhere else I put it. The less rules, the better. That's the lower energy. So how does this translate into doing electron configurations? So give the box orbital diagram for the nitrogen atom. 7 valence electrons, right? So here's the first thing I do. I just get the valence electron. The electron configuration. Then after I do that, I say, oh, here's a S with only 1 orbital, 2 electrons in it with opposite spins. Same thing here. Here's a p orbital, so it's got 3 orbitals. I got 3 electrons to go in there. So I'm just going to put them in different boxes so they don't get bunched up with each other. They don't have to follow the rules. And theoretically, all 3 of these boxes have the same energy. So this is a more accurate representation, but it's harder to draw than this is. So now you see nitrogen is this as the element. What about the only nitrogen ion? So nitrogen is right here. What does it want to do to become like a noble gas and stable? Gain 1, 2, 3 electrons to be isoelectronic to neon. So it's going to be the N-3 ion. Now looking at this, you see where those 3 extra electrons are going to go. They're going to go right in there. And why would it do that? That's a partially full subshell. That's more reactive than a completely full subshell. If I do the same thing for sulfur, sulfur Here's the electron configuration for sulfur. It's S2P4. So here I had to bunch up one of the electrons, but I could take that electron and put it there or there, either way. And what does sulfur want to do? Form the -2 ion to gain 2 more electrons to become S2P6, right? You can see exactly where those electrons are going to go. When those electrons go in there, you have a completely full subshell compared to a partially full subshell. Now, the atom is more stable. What about aluminum? Aluminum is a metal. If you look in the periodic table, all it does is form the +3 ion. So here's the aluminum electron configuration. And what about the ion? Oh, it's completely empty. Make sense? That's the stability right there. So I did it for bismuth. I did it for scandium. I did it for chromium. All the chromium ions. Okay. And then I have a whole bunch of summary examples over here. So a lot of practice right here because a lot of this stuff is actually pretty difficult to do. And here's another kind of an important example over here. Why does potassium and bromine react to form potassium bromide? Here's potassium. And in this case, I started putting Lewis dots over here. So Lewis electron dots are essentially every valence electron gets a dot. So potassium has 1 valence electron in a 3s orbital. So I put the 1 dot there. Now, is potassium stable? No. What does it want to do? Get rid of that 1 electron right there. That's what it did. What does bromine want to do? It's S2P5. Here's its 7 valence electrons. What does bromine want to do? Well, if it were to gain 1 more electron, then its subshells are going to be completely full. It's really isoelectronic to the next noble gas. That's stable. That makes sense? Both of these go from reactive to stable. So potassium gets rid of its 1 electron, which it wants to do anyway. Bromine takes that 1 electron because it wants to do that anyway. Now they're both happy, and now they both happen to be oppositely charged and attracted to each other. And so, yes, this is pretty difficult to do, but I showed it to you anyway. And we can actually use this to figure out now, why is iron not like a noble gas? Noble gases are S2P6, but iron is S2D6. That's full. This is not. No matter what iron does, it will not be able to satisfy this by being completely empty or completely full. And that's why it's not a noble gas. Okay, well, we went through all 7 of those things I wanted to point out. That's the bulk of what you need to know and know how to do. So you'll be asked to do stuff like this, give the box orbital diagram for the only nitrogen atom. On homework, I most likely will give you harder problems than on an exam. If you can struggle through the homework and learn a lot from that homework, then the exams will be much easier. So tomorrow what we'll do, it's like, how do we know all this stuff? Where does all this information come from? And that's what the rest of the chapter is about. And for the most part, textbooks wouldn't have the rest of the chapter. It's like, oh, just know this stuff. I can't function that way. Okay. So any questions so far?
That was quite a lot, Professor.
Yeah, wasn't it? Are you guys getting your money's worth?
that was a lot.
So by the way, for both courses, I put all the homework up. For 241, all the quizzes are up with due dates. And the due dates are in tests and quizzes. And I notice if I first put up a test or quiz and then I have to change the due date or something, it doesn't change in the grade book. I know one student was having an issue with that. But the due dates are in tests and quizzes, okay? So anyway, oh yeah, in exam 2 for biochem starts on June 22nd. And for Chem 100, it starts on June 29th. Okay. So if you got any more questions, just you can always email me. Or you can ask some questions right now.
When will we be getting back our exam 1 scores for the biochem class?
Well, the scores are posted in gradebook. Yeah. As soon as you submit your homework, quizzes, or exams, the score appears in gradebook.
Okay, thank you.
Okay, then. We'll stop here, and you guys have a great day. And tomorrow's Tuesday, so yeah, we can do it again at noon. Finish up
Thank you,
this chapter.
Professor.
Thanks, Professor.
So you
Thank
guys
you,
have a
Professor.
great day. Thank you. See you.
Yeah.